waiting to see the way the wind blows?
No, I had to think about it.
Okay, sorry if I rushed you. Okay, let's gotta think of it. All right, so. They look like they're sticking out about the same amount. Well, it does definitely seem to get down first. Don't think board bias is going to make up for that difference. So, congratulations to those people. So what, sorry?
Density? Density.
Not density.
The air.
Air doesn't, air does not really explain that being a tie or.
Oh, well, I guess I was thinking about I was thinking about the hoop one.
Oh, air getting caught in here?
Yeah.
It's not going fast enough really for air to make that significant of a difference.
So it feels like it's a matter of where the mass is more concentrated towards the center of the axis.
So the one more concentrated towards the center of the axis, the faster it is?
I would say like the reverse, like the more it's towards the outer, the slower it is.
Okay. That, we just said the same thing. Okay. Sorry, I missed the humor there at first. All right, so if I take well, we've seen that size does not seem to be of any significance. So now I have a hollow or thin-shelled sphere and a solid sphere. If that is correct, what you said is correct, which one will make it down first?
Big blue.
So are we saying, according to that big sphere?
Come on. Based upon what Logan's speculation is, the big sphere should make it down first because there's more mass at the center. That definitely was a bad one.
Looks like it went negative.
Yeah. And in fact, you are correct. So it's how the mass is distributed, which we sort of touched on a little bit earlier. It's not, so I don't view it as density, but I guess you could if you consider this is a much greater density than the air in the middle. So let's actually think about what's happening there. When they started, what was the kinetic energy?
Zero.
We have an object up here. So kinetic energy, 0. Let's make H is equal to 0 down here. So I've got some gravitational potential energy there. So if I took two objects that did the exact same mass, same size, same center, same height of the center, they'd have the same potential energy. As it rolls down the ramp, that potential energy gets converted into kinetic energy. Well, I have two types of kinetic energy here. I have the kinetic energy dealing with how fast the whole thing is moving, and I have a kinetic energy based upon its rolling. So I'm going to have a kinetic energy, like kinetic energy be 1/2 mv squared plus 1/2 I omega squared. I got these two parts. Again, this is dealing with how fast the center of mass is moving and how fast it's rotating. I have a set amount of energy I'm starting with, and it gets distributed between these two things. The more I have, more energy is required to rotate it, the less is left over to move it. I, for the most part, for things that roll, is going to be some number times mr squared. So what determines the moment of inertia really is that number up front. And the larger this K value is, K is just the letter I'm using, it's not some official term. The bigger K is, the more energy is required to get it to roll, less energy is left over to get it to move. So that's it from an energy point of view.
That's like what you talked about with this thing with the rod on edge, right?
Yes, yeah. So when I rolled the hoop, versus, there's an implied 1 there, versus the disc, the coefficient up front was greater for the hoop, it's going to take longer to actually move down the ramp. When I did the sphere, the solid sphere, versus the disc, well, that's smaller, that's larger, more energy went into rotating the disc than it did to getting the sphere to turn. Yes?
So my comment on them having different equations was correct.
Yes. Yes, my issue with it was the generalization of it. That was,
All right.
I felt too vague, but that was, you were correct. Now, what about size? Because I did the big disc and the small disc. Well, it turns out radius and mass don't matter. Let's just run through a quick sample here. I put it back. Back trouble. So let's take the disc. Let's assume it's a disc rolling down. The forces acting on it. Well, I have 3 forces acting on the disc. What are the 3 forces?
Gravity.
Better? Come on.
Weight.
Thank you.
Friction.
Gravity. You stop. Let's look at the small aspect. Yep, friction.
Normal force and normal force.
Now, I'm sort of making a claim, or at least heavily implied, that energy is conserved, but I got 2 non-conservative forces here. Let's think about that. If I have a disk that is rolling, weight is acting on the whole thing. But the friction is acting on the point of contact. Normal force is acting on that point of contact. Well, 2 issues here. 1, that point of contact comes off the table very darn quickly. So that normal force and friction are not acting over any particular distance. And second of all, that point of contact comes up. Yeah, it was going to be a brilliant demonstration, except lack of coordination. So I did that. So my hand, for the most part, is coming upwards. Not as brilliant as I was hoping for, but later on, perhaps we will all see the genius in it.
Was that a part of like your bicycle at one point?
No, it was here when I got here. It was a life when I found it. All right. So these do not do any work. The forces are, the non-conservative forces are there, but they don't do work. The only thing doing work is weight, which, as we all know, is a conservative force. Therefore, energy is conserved. And this is potential plus kinetic, gravitational potential, and then we actually have 2 kinetics. I'll just leave it generic for right now. Initial, UG fun plus K fun. I have 2 kinetics involved here. UG initial plus 1/2 mv squared initial plus 1/2 I omega initial squared equals, oh, I guess I could have made that substitution there. Go ahead and do that. What is the potential energy formula for that's associated with weight?
MGH.
And equals the same thing, but with final. final plus 1/2 mv final squared plus 1/2 I omega final squared. So just generic energies, beginning equals energy at end, and then I plug in the different types. I know it starts out with no kinetic energy, so those are 0 because it started at rest. Making height is equal to 0 at the bottom, so that's going to be 0. So I'm left with, I start out with all this gravitational potential energy converted into kinetic. As we look at the kinetic formulas here, I have 1/2 mv final squared plus 1/2 times, well, for a disk, that is 1/2 mr squared, omega final squared. And so now I have r squared omega squared, which is v squared. So I have 1/2 mv final squared plus 1/4 mv final squared is equal to mgh initial. Every term has mass in it. Mass goes away on all of them. And so we've gotten rid of the radius and we've gotten rid of the mass. And so in this particular case, we have GH, the initial, is equal to 3/4 mv squared. You're correct. That is not the m you want. So the final speed is the square root of 4gh initial. If friction were involved, obviously, we now have non-conservative work being done, energy is not conserved, but it turns out the mass is not going to matter anyway. Sorry, there is friction involved, otherwise it wouldn't rotate. If there were sliding friction involved. Because that, in an ideal roll, that is static friction. You don't want any sliding. If there's any sliding going on, then it all gets messed up. There was a lab I've done, it's been a while since I've done it, but where we took a ping pong ball and based upon how fast it went down the ramp, try to figure out what the thickness of the shell is. And the first time I did it, realized if the ramp is too steep, then it's definitely going to slide, and roll and slide. If it's too shallow, then any idiosyncrasies or small little bumps in the track are going to affect more. So there's some optimum angle at which we can minimize the hazards. And I think the angle ended up having to be something low like that. However, on that note, I know, just give you some a little teaser for what might happen on Monday. All this is great. It's because we throw a spring into it.
Roll the spring down.
Not rolling the spring, roll the ball down into it doesn't work on the board. To a spring. I got a ball, I got a spring. How far is the ball going to go down before it stops, the spring stops it? And then, if we threw friction into it, how far would the ball go? And the nice thing about it is that it involves the quadratic formula, and I know you're all fans. There we go, like that enthusiasm.
Yeah,
Yeah.